worries.
Unfortunately, we cannot clap like normal presentation, but as we did. Okay, so the next speaker is Dzmitry Kananovich. I hope I read correctly the name, from the Tallinn Technical University, the synthesis of new host molecules. So Dzmitry,
thank you, Roberto, for a nice invitation and introduction. So I'm ready to start. I hope you can hear me. And one moment. So can you see my presentation now?
Yes.
So it's fine, right?
Yeah.
Okay, then let's start.
You have to put in the presentation mode. Okay, now it's okay.
So sorry, something is wrong?
No, now it's okay.
Okay, so but okay. Oh, now it's fine. So hello everyone. My name is Dzmitry. So I represent Tallinn University of Technology, and we work with RENA. Basically, my part of work is synthesis of new host molecules, and I know that many of the initial partners, you're already familiar with the materials which we produce in our lab, but probably you have no idea how do we make them. And today, basically, the main point of my talk to give a kind of introduction into this chemistry, how to make these molecules. But on the other hand, instead of showing you boring structures and kind of reactions, I would like to stress on mostly on the challenges which we face on everyday manner when we try to synthesize these hosts. And basically, my background is synthesis. I'm a synthetic chemist. But before Initio started, I have never dealt with chemistry of this microcyclic host. And I would like to stress on that this chemistry is somewhat different from the normal small molecules I kind of used to deal before. And sometimes these specific issues, they are not so evident. And I'm gonna show you something regarding this today. So let's start. First, an introduction to the diverse world of microcyclic host, microcyclic receptors and supramolecular chemistry. They are diverse. They have different structures. We have a lot of vulnerable hosts here, like crown ethers and porphyrines, and also several quite complex quite complex on the first look architectures, and chiral molecules like cyclodextrins and cyclohexana hemicocurbituryls, which you know very well, I hope. And the first glance, this diversity looks remarkable and quite complex. But what is common from the point of view of a synthetic chemist here, that basically all of this diverse world is made of quite simple uniform monomers. From the synthetic point of view, this strategy is pretty straightforward. Just make kind of oligomerization reaction and you will get your microcycle. Of course, the efficiency of this synthesis could be different. For example, if you recall synthesis of porphyrines, a common method, for example, to make TPP porphyrin is the Rosamund method, which is maybe not so efficient, or we can make it more beneficial. Synthesis of microcycles, like in the RENA's case, we can use a template-controlled synthesis when we have an anion as a templating agent, or also this so-called dynamic covalent chemistry. So it could be pretty efficient in this case, but nevertheless, doesn't matter what is your outcome. It's just a one synthetic step. So all the starting materials are relatively simple, easily available, and you can get it fairly easily, just in one step. And today I would like to focus not on that actually, not on that chemistry, which is quite very well known already, but I would like to focus on post-synthetic modification or derivatization of these microcycles, how to produce new molecules out of these easily available uniformly functionalized microcycles. And here at this point, actually, this uniform structure is not advantage anymore. It's an obstacle. If you think about, say, monofunctionalization, if you like selectively functionalize only one unit, you face so-called selectivity problem, how to make it selectively only at one unit. And quite unusual problem also, if you would like to fully functionalize, but doesn't look as a challenge, you face so-called, as I can call it, reactivity problem. And I will tell about this in more detail today. And besides this chemistry-related problems, I have to point on that we have kind of accompanying practical obstacles, like sometimes limited solubility of the starting materials or products in the common organic solvent, and also some complications with analysis. So to do this chemistry, you really need to have a good analytical chemist in a team. And first of all, what about the motivation? What we need to do it at all? So the reasons could be different, of course. For example, fine-tuning of properties like solubility, immobilization, solid support, via covalent linkage, whatever. But what is the most relevant to the aim of our project is a design of robust sensor, which will work in any media. When you can covalently link, for example, your chiral microcycle and the receptor, optical signaling unit like porphyrin, right? So it makes the sensor more robust. And I will show just an illustration of this, why it's crucial for efficient sensing from one of the very recent literature example, which was published like a few weeks ago. In this case, in this representative example, the cucurbituryl molecule was covalently linked with a dye, and it was beneficial to make an official sensor for some drug molecules. Why? Because when you have only a covalently linked supramolecular aggregate, it easily dissociates in saline media. When it's already covalently linked, it can't happen, and you have then working sensor which can work in saline media. And now, briefly, I would like to outline the main challenges which we face, say, during the monofunctionalization. Also, I know that many of the teams, they work with monofunctional compounds we produce. I would like just briefly outline this topic today and not to go into detail, otherwise my talk a little bit too big, out of time. And the main challenge here is a selectivity challenge, because when you have this uniform monomer units, it's very hard to stop the reaction at the first step, right? When you have it's very hard to stop the reaction at the first step. When you have, say, monofunctionalized material, it goes further. And in general, because these rate constants are usually more or less the same, you always get a mixture, so it's unavoidable. And to get this monofunctionalized compound, you either need an efficient separation technique or a bit better solution, you can control reactivity. So that means that upon this extent of this reaction, upon progressing, this reactivity should drop. So rate constant, for example, in the second step should be lower than at the first step. That's the ideal case, how you can control it. Another, as I can say, strategy is to form this, for example, monofunctionalized microcycle by condensation with mixed monomer. And again, in this case, if your monomers have a kind of similar reactivity or equal reactivity, you will face a statistical distribution of products anyway. So again, you need to either to separate. So this paper published by Vladimir Shintelar shows very nice example of that. You need to separate anyway. You can control somehow distribution of product by ratio of monomers, by molar ratio of monomers in the mixture, but it's unavoidable. There are some also tricks how you can control it by some kinetics and thermodynamic issues. It's possible, but quite challenging. And maybe, I hope, I will tell about that in more detail in future. But today, I would like just to show one literature example, which is quite representable. So I like it very much. It's monofunctionalization of Q-curbituryls. And basically, this is kind of very user-unfriendly molecule for a synthetic chemist because it doesn't have any reactive functional groups. And the only thing you can do here is it's the radical reactions, like radical hydroxylation. And of course, this reaction is very hard to control. You always have a mixture of products, and the yield of the target products is rather low, around 14%. You have to separate it from starting material, from the other hydroxylated hemicucurbituryls. And also, there is a huge problem with solubility. And I would like to complain a bit here because we have a kind of misunderstanding with the people who study supramolecular properties of the compounds like this. So they often posit a kind of water-soluble compound. And for them, it's water-soluble. If you can get, say, millimolar concentrations, already fine. For us, for synthetic people, it's totally insoluble, it means. So you have to do this reaction in aqueous media, but you need to use kind of large volume of solvent. And it's not, in this case, it actually quite frequently happen, I have to say. So the solvent-based reactions not always have advantage. And another problem, as I told, is analysis is in this case also nicely illustrated. And for example, in one research published in 2015, it was claimed that the yield can be over 95% in this reaction, almost quantitative, which looks like really fantastic. But later it appeared that it was just an error with NMR data interpretation. And the actual yields are pretty low. So, and it looks actually reasonable. So the lesson which we can learn from that is that never trust one analytical method, especially NMR. I have to confess that common techniques when we use in organic chemistry during synthesis like NMR, it's not enough here. And I will show how we can deal with that in my talk. And today, as I told, I would like specifically focus only on one feature, like on the one reaction, like total functionalization, where we meet so-called reactivity problem. So what's the problem here? It doesn't look like a problem for the first look, okay? You just need to run your reaction till the completion. Just what's the problem? Just go ahead. But if you have a more detailed look, and for example, if the reaction produce per one monomer unit, your reaction, derivatization reaction, produce 97% yield, which looks pretty good for a synthetic chemist, you must keep in mind that you have to repeat this reaction actually n times. And that, what does it mean? At the end, you have yield like this, 0.97 in the power of n. And if n, for example, equals 6, the yield of the final product will be only 83%. So looks maybe not so bad, but that's only one side of the problem. Because from the other side, what will be the rest? What will be the 17%? 17% will be all these guys before this hexafunctionalized product. So it will be a mixture of everything. And taking into account that the properties of these intermediates are very close to the properties probably of your product, it will be a nightmare to separate. So what is the solution. The solution is obvious. You have to get nearly quantitative yield per step to make this reaction efficiently. How you can attain it? There are only two ways. So basically, either you use an excess of chemicals, which is pretty common sometimes, and by using this excess, you run your reaction till completion. This is a good solution when you have, for example, say, easily available compound to modify your microcycle, right? Some cheap and volatile, then you can easily remove excess. So then it's not a problem, right? But sorry, but if it's not the case, what to do then? So the only solution in this case is only to raise the reactivity, to raise the yield per step by improving your chemistry, the chemical output at each step. And I would like to present today a case study of this. And one of the molecules we work with right now, it's biotin 6-uryl. This is a microcycle which was discovered by Michael Pitkov group, and it can be easily produced in multi-gram quantities by condensation of biotin, which is actually a vitamin and easily available, with formaldehyde. And this process is catalyzed by hydrochloric acid. It's also a template synthesis. So this compound is easily available. And in contrast to cucurbitaryls I showed before, it's okay. It's much more user-friendly molecule because it contains already a number of functional groups which you can play with, you can modify. So, for example, carboxylate or this sulfur here. And the same group, they showed already that you can take advantage of this and you can modify properties of your molecules. For example, you can make esters by using alcohol in excess, like a solvent. You can make methyl ethyl or say butyl esters, or for example, you can oxidize it with hydrogen peroxide, with also pretty efficient reaction. So we can make sulfone. And since we have this compound and we in big amounts you can produce them, we started to think how we can use the advantages of this carboxylate group to make maybe another structures and maybe more complex compounds out of it. And one reaction which looks pretty suitable for this purpose is amide coupling. So why? Because of the two reasons. First reason that we have huge selections of amines, so you can actually find a lot of them commercially available, and basically it means that you can attach whatever you need. And the second reason is this: these amide coupling methods are very robust, they're very well developed. And how it's done, this state-of-the-art approach, of course, you can't do it like direct condensation because it's too unfavorable. It requires harsh reaction conditions. It's commonly made through the activation of carboxylate to replace OH to a better living group. Like historical method, you know, like this making acyl chloride or something, right? But nowadays methods, they use in situ activation, so you can mix your carboxylic acid with amine already and to add some amide coupling reagent which performs this activation in your reaction mixture. And there are numerous amide coupling reagents, numerous types. There are about a few dozens, maybe up to 100 already developed. Different type looks chemically different, like carbodiamides or uranium derivatives, but they all work same way. So basically they activate your carboxylic acid. Okay, so how we can apply this transformation now to our purpose for derivatization of biotin 6-uryl? For example, let's imagine that we would like to couple this carboxylate, all-6 carboxylate, with C-terminus protected amino acid like phenylalanine. Of course, in this case, we we can't use a huge excess. We can't use this compound as a solvent or something. So we have to use it in almost stoichiometrical amount, just a bit more maybe. Like here, 6 equivalent. It's a bit more than stoichiometrical amount per one carboxylic group. And how to make it? So the usual approach is pretty straightforward. So you just need to select a coupling reagent, a base to deprotonate carboxylate, and of course a solvent, right? And the most common trio which you can meet in many amide complex, including peptide synthesis, is like shown here. So we have HA2 as a quite powerful coupling reagent, D-isopropyl ethylamine as a base, and solvent like DMF. And I already talked a bit about the problems of solubility. And I have to say that in this case, the DMF or similar dipolar aprotic solvents is the only choice you can use, because this compound is pretty hard to dissolve in just other volatile organic solvents. So we really stick to this DMF. And what will happen if we will run this reaction in solution? As I told, NMR is basically almost useless here because you can't distinguish the product and your starting material. And luckily, we have in our group brilliant analytical chemist, Tatiana Shalima, who established HPLC analysis for this particular reaction. And what you can see, so basically, yes, you have your hexa amidated product and approximately 78% yield, but it's contaminated. It's contaminated with everything else. We have penta, tetra, 3D, mono, and even starting material here after running this reaction in solution. So the problem is, first, insufficient coupling efficiency. So it's not enough. The yield per step is not high enough. And second, solubility. We stick only to aprotic dipolar solvents like DMF, which is not terrible, but not pretty convenient to use because they are not volatile, they are toxic, and not so good if you're gonna upscale your synthesis. So how we can actually solve this problem? And it might look pretty weird from kind of conventional modern chemistry, but if you go from solution to actually solid state, it might be pretty advantageous to increase your chemical yields and also to avoid any solvents. So looks weird because modern chemistry, as you know, is totally solution-based, but we have to recall how the chemistry started, right? So basically, solid state reactions, perhaps that's how the first chemical transformations were made, by grinding the solid reactants in alchemist lab, like you can see in this nice and growing from 17th century. So it's foundations of modern chemistry, by the way. Of course, this way of making a reaction with mortar and pestle is a bit outdated. It's good for medieval times because it needs patience and some muscle strain. At least 3 years ago, when I asked one of my PhD students to do one mechanochemical reaction by grinding, he gave up already in half an hour. So he was tired. It's really difficult to grind your reactants. But hopefully, due to the technology advance, we have some 21st century device, and we have a rapidly evolving field of so-called mechanochemistry, which actually studies how you can make your chemical transformation and chemical transformations in solid state and activate your reactants without solvent by applying some mechanical force. And so this 21st century device, shaking wheel, we have in our lab, and we can apply it to the synthesis. And I will show you briefly a kind of advantages which this mechanochemical synthesis brings in comparison with solution. So As an example, I am just showing the one amide coupling reaction, which is actually, say, moderate, difficult to perform. Why moderate? Because amine here have low nucleophilicity, so it's not so reactive and has this is aromatic amine with electron withdrawing substituent. And if we run this reaction in solution, follow the conventional protocol, what we have to do? We have to, of course, select coupling reagent. In this case, it's another uranium type coupling reagent, which is actually very similar to HATU, COMU. We have to take again smelly and unpleasant organic amine like d-isopropylethylamine. We have to take DMF as a solvent. And this reaction, to make this reaction, you need to stir it for at least 20 hours to get at least 70% yield. So this is the maximal conversion you can get. And the reason for that actually is that also this reagent is not so perfectly stable in solution. It slowly degrades, interacts with moisture, and so on. So long story. And quite modest yield, right? So now let's compare with mechanochemistry. You do it mechaноchemically just by grinding solids. So again, we have coupling reagent, of course. This time we can replace our organic base with inorganic one, which is very cheap and safe. Of course, it's not soluble in organic solvent, but you don't care about solubility anymore. And it's essentially a kind of solvent-free technique, but a few drops of liquid usually you need to add, and it's so-called liquid-assisted grinding, which very accelerates the reaction and also makes it more efficient. In this case, we need to add just a few drops of ethyl acetate. And what do you have? You just need to mill it for 20 minutes, and that's it. The reaction is done. So it's much more rapid than its solution. So 70% conversion, you have already less than the same conversion like in solution, you have less than in 5 minutes. So it's more than 200 times acceleration. And basically, what is also important, the isolation protocol is pretty simple. You just need to wash your solid with water, and that's it. It's much more easy than to make isolation here than to remove this DMF, which is very hard to remove. So you have to extract, you have to wash with water, then you have to make column chromatography. A lot of actions here. Just wash and dry, and that's it. So mechanochemical synthesis, it has many advantages like fast reaction rates, so enhanced reactivity, what we actually also need for our aim. You have no solubility problems, no solvent compatibility problems. It's high yielding. We have easy isolation protocol. We easily obtain pure products, and it produces less waste and more safe. So it's good from the point of view of green chemistry. And if you want to recall the first principle of the green chemistry, it teaches us that it's better to prevent waste than to clean up waste, right? So, and for initial, I can add it's better than to sense waste, right? So our project aim is to sense pollutant, but not to make more of them, right? So pretty a lot of advantages we have here, and I would like to show you that it's also practically pretty convenient. So I can show you a short video, but one moment. Okay, so how it's done. So basically you load your solid reactants into a so-called milling jar with 3 milling balls. And we just fix it in the instrument. And it shakes like approximately with rates 30 times per second. So it's very violent shaker. And then what you have in 20 minutes. the reaction mixture. And then the only thing we have to do is just to transfer it to the filter and wash with water and to dry. And that's it. You have a product with quite a high purity. And this I like very much, one picture which worth 1,000 of words. So if you compare NMR spectra, this the same product made in solution and by mechanochemistry. Here in solution, it's after column chromatography, after purification. So as commonly you can see here, these contaminates of your solvents from chromatography, you still have to dry it. But for mechanochemistry, this is a crude product, and you see it's perfectly clean. This also works for hard cases, like shown here. So, case of hindered carboxylic acid and extremely pure nucleophilic amine. Basically, also accelerates this reaction, mechanochemistry. But of course, we need to select a bit different conditions, more reactive combination of coupling reagent and base, which was discovered by Beltner group and reported recently. This TCFH reagent and NMI and methylamidazole as a base. So it works, and it works again approximately 24 times faster than its solution. So now how we can apply this knowledge to our aim to functionalization of biotin 6 uril by the amide coupling. So you can have a look on the reaction, and at the first look, it looks nothing problematic here, right? We have no steric hindrances. We have no problems with electron deficiency, so it's pretty nucleophilic reaction partner. So what's the problem? It should be a very easygoing reaction. But as I already mentioned, you have to do this reaction 6 times, right? So we have to go through the 6 steps. And this makes this case also difficult, as if we were here very hard case of amide coupling, but you can see on the results. So if you apply like these reaction conditions, which is suitable for more normal coupling, but not reactive enough, you have a mixture of everything. And the yield of hexamide is rather low, 16%. And again, we have to go to highly reactive reagent combination like TCFH and methylamidazole to get conversion about 98%. Also, as I told you, this liquid green zinc additive is very important, so it plays some role. So without it, you have generally lower yields of your reaction. But it works, and it gives now very nice reaction outcome and pretty clean HPLC from the crude product. So by applying this, we have developed finally the suitable, very convenient and practical mechanochemical amidation protocol, how you can derivatize this particular microcycle, for example, with amino acids. So it doesn't require huge excess of coupling partner, so it's nearly stoichiometrical amount. You don't need to care about solubility or any solvent, so basically you do it in a solid state without any solvent. And you have pretty nice conversion by HPLC, so just subtle contamination with failed sequences, failed unamidated project, and so on. And pretty straightforward and handy workup and purification procedure. So you can make your material finally in quite a high yield and quite a high HPLC purity. So this is one representative example, but of course we can apply it to add some other amines, and we can produce some materials which some of you already familiar with by attaching these different amines. And some briefly conclusions, what we can learn from this. So basically, challenges, first of all, right? So Microcyclic receptors, there are numerous. They are generally quite easy to make, but their subsequent derivatization is rather difficult. So with monofunctionalization, we commonly face selectivity issues, how to perform your reaction selectively. For complete functionalization, also it doesn't look a problem, but you face so-called reactivity issue, how to get high yield of your product. And it's always accompanied with additional complications like solubility, and you have to really have a trustful analytical method to analyze your reaction outcome. So the solutions, mechanochemical synthesis can be advantageous in this case. So it eliminates some problems like the solubility, solvent compatibility, enhances reactivity, what is important for complete functionalization. It's convenient for isolation of pure product, and it's good from the green chemistry point of view because it's safer and produce low waste. Of course, I have to highlight that it's not a magic bullet, of course, but quite a nice tool to deal with this microcyclic chemistry. So I hope the story of this chemical synthesis will be continued. And at this point, I would like to stop and thank you for your attention. It's time to go to the acknowledgement section. So I would like to acknowledge first the Taltech supramolecular group. You can follow our activities in social media, like shown here. More specifically, I would like to acknowledge several persons who were deeply involved in this synthetic work. Of course, Rina, Professor Rina. I would like to thank her for her enthusiasm and inspiration for the whole team. And of course, I'd like to acknowledge our PhD students who made experimental work. So all the synthetic part of the project is done actually now by Tatiana Dalidovich, and it was assisted greatly by Kamini. Tatiana Shalima is our brilliant analytical chemist who really helps a lot to understand what do we have as the outcome of every reaction. Without her help to work in this field, I can't imagine how we could work without the good analytical chemist. And also Dr. Marina Kudryashova, who assists us with anima measurements. And for the whole initiative, I would like to thank you for keeping our lab busy. We always have to do something, to synthesize something. So we have work because of you. And of course, several funding sources which makes our work possible at all. So thank you.
Okay, thank you, Dzmitry, for the inspirative presentation. And there are questions? No? Okay, so we can have now we thanks again, Dzmitry, for the presentation, of course, and we have now the half-an-hour break, so we'll meet again at 11:30.